tasks that we give the students each summer. And so these are the mentors that came out this summer to work with our students. So on island, key people are Mike Rosen and Ross Hansen and Tyler Garzo. From John Hopkins Applied Physics Lab is Tom Johnson. And Tom is also a former Shoals staff and Cornell alum and just longtime participant in this program as well. From UNH, Martin Wolznick, Isabel Menderos, and Ruzbe Gazmi all came out and mentored the interns. From Unitil, Justin Urick, Alex O'Mara, and Greg Walsh gave time and expertise. And then finally from Seacoast Consulting Engineering, Lee Consavage, who has also been mentoring for many years. And we appreciate all of these mentors who give generously of their time and their expertise to help solve problems and teach and mentor these interns this summer. So I want to, these next two slides are my final intro slides, and I just want to cue up what we're doing and who's doing it. So we're going to do 2 rounds of 25-minute presentations. It's a mix-up of smaller presentations, but a total of 25 minutes of presentations followed by 15 minutes Q&A. We'll provide a 15-minute break between those 2 rounds so you can go get your second Shoals cookie or your cup of coffee or whatever you need. And if you have questions along the way, please use the Q&A button. You know, if there's 5 minutes into the talk and a question is burning in your mind, you can put it right in Q&A and we can ask it at the end. But you will also be able to unmute yourself and ask questions directly so that we can have a little bit of a dialogue. Like most of you have been to this on the island, know that we have a little bit of discussion and we're really excited for that and encourage that. So your comments and your questions are very, very welcome and a part of this. So our interns this summer, Brooke Elzweig came to us from the University of Colorado, where she graduated in 2020 with an undergraduate degree in environmental engineering. So she was clearly one of the 2 engineering interns this summer. Zachary Robarts is a graduate of UNH this year. Congrats on that. And also an environmental engineer. And then Anna Keiffer is a rising senior at Cornell in environmental science, and she was the communications intern, and she'll be presenting her work along the way as well. So I'm going to stop sharing and I'm going to turn it over to the interns to start sharing.
Thank you, Jen. If you wouldn't mind allowing participant screen sharing, I can get the presentation up and rolling.
Gotcha.
You should be all set, Zach. Go ahead and give it a shot.
Thank you. Now, Brooke's going to start us off introducing our assignments.
Yeah, Jen, thank you so much for the introduction. Zach, Anna, and I are very excited to share our work and findings with you all. With that being said, let's get started. I'm just doing a general overview of the assignments we'll be covering today. So we're going to start off by looking into the upgraded refrigeration system and comparing its efficiency to 2018 and 2019 data. And then from there, we're going to lead into the reverse osmosis and the well, where we're going to identify trends and relationships in regards to total island water usage. We will then broaden our scope by looking into the actual power output of the brand new 10 kilowatt Berge wind turbine and compare those findings to theoretical values. And lastly, we are going to analyze the ratio of green energy utilization rates to diesel generation on the island and look into how we can improve the connectivity of Shoals independent green grids.
So the first topic that the engineers are going to talk about is the new refrigeration system. And I'm going to start this section off by showing you a video that I made. It's a very quick one. It's talking about the new refrigeration system. So wait, pause it. I can't hear the audio.
Thank you. Thank you.
the average home requires between 600 and 650 kilowatt hours a month. So 680 kilowatt hours is more than enough to power a home.
All right, great video, Anna. There couldn't be a better way to introduce our first project, which is the refrigeration upgrade evaluation. So just to give you guys a quick background, SML's commercial kitchen is equipped with a walk-in refrigerator and freezer for food storage. And based off of data and recommendations from 2018 and 2019 sustainable engineering interns, we wanted to upgrade these refrigeration systems with new compressors, evaporators, and piping to improve efficiency in the fall of 2019. Our first deliverable was to work with SML staff to set up metering to monitor the energy usage of the new refrigeration system and compare those findings with the 2018 and 2019 data. We also calculated the energy used by the refrigeration system as a percentage of SML's total energy consumption, and then documented those efficiency increases realized through the installation of the new equipment. So to get started, this is an example of how the fridge compressor works and draws power as it attempts to self-regulate the temperature inside. When the fridge is open, the temperature increases and spikes in the power follow. This graph shows the active power, but it's important to note that there is more to AC current than just the active power. And as a result of the fluctuating sinusoidal pattern of an AC current, there are inherent inefficiencies in power distribution. Nevertheless, we're able to measure these efficiency gains through VARs and watts provided by the Fluke meter, which ultimately helps us calculate volt amps. So a good way to visualize this is through the beer analogy. So everyone visualize a cold glass of beer. Pretty much the beer represents the active power, which is the watts. So this is the useful power. Essentially, it's the energy that is doing the work. This is the part that you want to drink. The foam on the top represents the reactive power, or the VARs, which is wasted or lost power. It's the energy that's being produced but isn't doing any work. You don't really want to drink this part, but the foam ends up on your upper lip anyways. And lastly, the mug is the apparent power, which is the volt amp. So this is the value we're trying to find. It represents the demand power or the power being delivered by the utility. And then all these values can be related by the right triangle, which is here on the right side of the slide. And yeah, we're able to calculate volt amps using a Pythagorean theorem where both watts and VARs are known.
Now, talking a little bit about our methods, as Brooke mentioned, we used the Fluke power meter, one of which models is shown on the right. And before we arrived this summer in early August, Ross did us the favor of collecting the power draw on each of the 4 components we were interested in looking at, those being the fridge fans, fridge compressors, freezer fans, and freezer compressors. And he analyzed with the Fluke meter, took power draw of those 4 components for 1 week each, providing us our data for this analysis. The data was compiled onto USB and analyzed via the Fluke instrumentation software with the help of Justin Ulrich from Unitil. And this Fluke meter collected both VAs and watts, and we were able to compare this data collected earlier this summer to the data that was collected by previous interns in 2018 and 2019. Quick overview of the results before I dive a little deeper on the next couple slides. You can see the total system active power of the entire unit was just about half a kilowatt. And the system apparent power, which was that power delivered by the utility, was almost 1 kilovolt amp. And over the course of 1 week, this refrigeration system uses about 87 kilowatt hours. We highlighted on this slide the individual efficiencies realized in the active power. You can see the fridge had a massive increase in efficiency, 77.6% as that system as a whole, while the freezer was slightly less, but still drastically reduced by 44.7%. Overall, the system was 2/3 or 66.1% more efficient in 2021 than it was in 2018, which is a massive improvement. Now, this chart is more in depth onto specifically the active power efficiencies realized. You can see the fridge fans realized the largest drop in active power draw by almost 87%, and following closely behind was the fridge compressor. The freezer, although less efficiencies increases, still decreased with, again, the total system active power draw reducing by 66.1%. Moving on to the apparent power, unfortunately, the 2018 interns did not leave us this data specifically, but we were still able to compare 2021 data to 2019 data. And you can see, again, that those fridge fans are carrying the bulk of this reduction in kilovolt amps with almost 80% of efficiency increase. The system as a whole reduced its apparent power draw by 48%. So in conclusion, the efficiencies realized by the upgrading of the piping, the condensers, and the fans on both the fridge and the freezer reduced the apparent and active power by 48% and 66.1% respectively. And this resulted in the active power use of about 87 kilowatts per week, which represents, when strewn across the entire summer, represents about 3.8% of the total island energy use, which is a drastic improvement from the old system. Another important thing to note is temperature. We looked at the average temperature of the air in 2021 compared to the weeks that the data was collected for this year and 2018 and 2019. And the temperatures were actually hotter in 2021 than they were in either of the previous 2 years of data collection. Now, if you remember the power chart that Brooke showed at the beginning, while that fridge uses active power to regulate its internal temperature every time it's opened, the fridge would use more energy while the ambient temperature is higher. But this was not the case because the efficiency realized by the replacing of the parts still drastically reduced the power draw. While this information is great, there are still more efficiency increases that can be realized. And this can be done both in the use and the physical characteristics of the system. Strip curtains can be installed on front of the fridge so that every time it's opened, that cold air has a little bit of a barrier and doesn't just flow into the kitchen. And secondly, maybe the kitchen staff can take care to reduce the amount of openings, or maybe during food runs, really get that food in as quickly as possible to reduce the amount of time that fridge is kept open. That will increase the efficiency and further reduce the power use by that system.
Okay, the next project our engineers are going to talk about is the RO. And again, I'm going to start this off with another video. Hi, welcome to Shoals Marine Lab. We are an island in the Gulf of Maine off of the coast of New Hampshire and Maine, where we study marine sciences and sustainability. Being sustainable means to be able to live without depleting resources for future generations and being mindful of what we use. While it's super important for all of us to be sustainable every day, it's extra important to be sustainable here at Shoals Marine Lab because we're an island with very limited resources. Despite the limited resources, you know what we do have a lot of? Wind and sunlight, which is why we have a wind turbine and a lot of solar panels. We get the energy to power the island from the wind and sun, but that still leaves us with how we get our fresh water. Although we are on an island surrounded by water, our fresh water supply is extremely limited because, well, we have an abundance of salt water and not so much fresh water. We do have a well on the island that can supply us with fresh water, but it relies entirely on rainwater, so it is also extremely limited in terms of how much fresh water it can provide for the island. So the question we have been trying to answer is, how do we get enough fresh water to supply the entire island from salty ocean water and also work on not wasting any energy from the solar panels? And that answer is a process called desalination. Desalination is the process of removing salt from ocean water. At Shoals, we use a reverse osmosis machine that removes salt from water to make it drinkable, also known as live stream water purification system, and also commonly known as the RO.
This year, our engineers have been working to find out how to use every last drop of available energy that we get from the solar panels by transferring the surplus solar energy into the RO to make as much fresh water as we can. They've been looking at the daily water use, rainfall data, energy usage of the RO, well water data, electrical demands of the RO, etc., so we can rely on the RO as more of a mainstream water source and making sure that it is still efficient and powered by the sun. Shoals Marine Lab is working to maximize its use of renewable energy by making sure that not even a drop of it goes to waste. We are making sure that our solar energy is either used by the island or by cranking out fresh water from the ocean. While one RO isn't going to change the world, the concept of not wasting green energy most certainly will. Thank you so much for watching. Bye!
That was another great video by Anna helping us introduce our next project. But before I go into this, I do see that Hal has a hand raised. Would you like to ask your question now?
Sure. My question goes back to the part of the presentation on refrigeration upgrades and temperature. And your excellent presentation. And I get what you're saying about upgrades, power consumption versus temperature changes in 21 versus 2018 and 2019. But your take-home message was for staff to limit openings of the refrigerator and the freezer down the road. And I would suggest that our experience in 2021 with reduced numbers of staff and students, there were perforce reduced numbers of openings of the refrigerator and the freezer. So does the information you collected allow you to weigh the trade-offs of the efficiencies which have been produced versus the increased numbers of refrigerator and freezer openings that would be expected when the island restores what I will call a more normal island population?
That's definitely something interesting that I didn't even think of until you just brought it up. However, while the staff creates large-scale meals every meal, while that scale does fluctuate based on the number of people on the island, they still have to create these large meals that involve a lot of ingredients, and so they go into the fridge. The thing that comes off the top of my head is that they wouldn't actually open it that much more for a larger meal because they still need the same ingredients. They still need to go into the fridge to get these ingredients. But I think that because it was a 66% decrease in power, I think that it still paints a pretty good picture of the efficiencies that were realized, while also considering that there were higher temperatures.
Okay,
that is definitely something interesting that people could look at potentially next summer if there are capacities increased compared to this summer.
Okay, thank you.
Thank
You're
you.
welcome.
I want to jump in. Thank you so much for that question, Hal. And I want to remind people and also let you know that I made a mistake saying there was Q&A on this call, and there's not. So please grab a piece of paper and write your questions down, and we'll take questions at the end of their presentations. So let's save the rest of the questions, which we want to hear and definitely want to discuss till they're done with this presentation, and then we'll get into the 15-minute Q&A. So thanks everyone for that.
Understood. Thank you, Jen. Okay, so let's get into the reverse osmosis and the well. So a little bit of background for you all. Shoals' primary freshwater source is a dug well that relies on rainfall for replenishment. But in 2019, Shoals purchased and installed a brand new reverse osmosis unit that desalinates seawater to provide an additional source of potable water for residents on Appledore. And as we all know, freshwater is a limited resource for most island communities. So that's why it's important we find a way to best maximize our usage of water while on Appledore. Our goal for this project was to help Shoals quantify the relationships between the reverse osmosis and the well water production. We did this by documenting daily inland water use, daily RO water production, as well as the daily volume of well water treated. And then we also looked into the energy usage of the RO compared to the well, and then monitored daily well level and rainfall data, as well as precipitation. But before we dive into our findings, I want to do a brief overview with the simple schematic of how the reverse osmosis system works for us on Shoals. So as you all know, RO is a water purification technology that utilizes semi-permeable membranes to remove ions, molecules, and larger particles from drinking water. The salt water enters a 1.5-inch pump, where you can see this at the saltwater inlet, and then is reduced to a 1.25-inch booster pump before passing through a pressure leak valve. It then trickles down into the media filter, which is the first step of pre-filtration. During this process, salt and gravel help to filter out dirty water and larger particles that we definitely do not want to be drinking. It then enters the machine through a 1-inch class flange RO stand connection and goes up through a cleaning valve to clean the membranes. Once it's there, it passes through a pressure valve before entering the CF1 20-micron cartridge filter and then into the CF2 5-micron cartridge filter. At this point, nothing is larger than 5 microns. And then from there, it passes through a high pressure pump at around 60 PSIs. At this point, we've hit the actual reverse osmosis process. The pressure quickly increases to 600 to 900 PSI in this high pressure manifold to condition the water. It then passes through a 3.25-inch tube into the first membrane per the pressure vessels, which are up on the right-hand corner. The clean water goes through a salinity sensor and a conductivity meter to calculate the total dissolved solids in the water. If the conductivity meter reads that the water is above a certain salinity, then it'll be moved to the brine water outlet and then processed again through the second membrane and pressure vessels once again. Oh, and by the way, the FM2 permeate flow meter shows the flow rate of gallons per minute, and then the conductivity meter helps to control the solenoid valve. And then lastly, the excess salt water, so the really, really salty water that made its way past the pressure vessels, passes through a brine flow meter and then to a cleaning valve and then out through the waste brine outlet. So this is our first graph, and it represents the gallons produced of the well and the reverse osmosis system. As you can tell, the first few days, there is no RO data, and this is simply because we didn't start running the machine until June 16th, 2021. As a result, we weren't able to collect a full month of data for June, but we were for July. Nevertheless, RO produced about the same amount of gallons for June and July, which was roughly 15,000 gallons. This is due to the fact that we ran the RO about 7 hours in June, whereas we only ran it for 4 hours in July. And then, this led to a total percentage of 39% in June and then 41% in July for contribution to the total water treated. And then for the well water treated, that was about 22,700 gallons in June and then 21,500 in July. It's graphed in conjunction with RO, and so we're able to see that the daily volume of well water treated did surpass the daily RO water production by about 61% and 59%. Now this graph displays the monthly water use at SML, which is heavily dependent on the number of residents on the island. Due to COVID-19, SML had to significantly reduce the number of students on the island and the number of classes that were available for the 2021 season. And as a result, Zach and I had assumed that there would be a significant decline in water production for 2021. But looking at this figure, it doesn't appear to be the case. The average water production for May was about 11,500 gallons. For June, it was 37,000 gallons and then 36,000 gallons for July. Compared to 2019, May had 22.3% less water use. June had 33.3% more, and July had 17.5% less. As a result, there aren't really any discernible trends in the daily inland water usage. And now this figure reveals the correlation of the well water treated, the RO produced, and then the total island usage from June all the way to August 2021. And as we can see, the total island usage is probably assumed to show the capacity of water for each day, but that's not necessarily the case, as evidenced in spikes in the well water treated. The data does show that the well water treated is pumped into the cistern, whereas the total island usage is what is pumped out of the pressure tank. Therefore, the water might not be used the same day that it's treated, and that's why total island use isn't fully correlated with well water treated. There is a specific anomaly to point out though on July 4th and July 9th. We're not sure what this is from, but we suspect it's from pressure cleaning or excess water usage, prepping for incoming students, or maybe it's just the island engineers prepping the pressure tank. So we're not sure, but this is what we were able to find.
Now, I'd like to highlight something that Brooke said about the percentage of the RO versus the well production for this summer, and that due to the runtime differences between June and July, the percentage of water produced from the RO was roughly the same for both months. And I'll touch on that later as well when it comes to running the RO and the best practices. But first, I want to pivot to the energy consumption of both of these systems. And you can see that the well produces water at a drastically lower energy demand than the RO does, at less than 1 watt-hour per gallon, which is really just a drop in the bucket in terms of energy usage, while the RO uses about 21 to 26 times that energy consumption per gallon of water produced, depending on what run settings it is run at. Now, to obtain that well electrical usage, we use the fluke meter on the well pump, and this pump activates once the cistern that contains the water to be chlorinated reaches a certain drawdown level, activates a pump that runs at 17.6 gallons per minute from the well. It runs for about half an hour and draws just over 1 kilowatt during that time period, resulting in just over half a kilowatt hour for that time period. Now, strong contrast to the RO, which in the beginning you can see a sharp increase in the kilowatts drawn, upwards of about 4.3. At some of the higher RO settings, it can reach 4.6 kilowatts, but it also decreases over time as the RO is run continuously, which indicates that if the RO is going to be run on any given day, it should be run for a long period of time to maximize this energy usage. Now, in terms of water production for the island's usage for the whole summer, the average daily water use this season was about 1,245 gallons per day. And while the RO can keep up with this demand if run for about 7 hours every day at its normal 3 gallons per minute, this is not what we would recommend. And that is because it uses much more energy than the well. If the well has enough water in it, we can tell that by the meter that was installed. We know the approximate water level. Then the well should be the primary source of water for the island. On summers that may be drier, we suggest running the island off of the well water in the beginning, and once that well level meter reaches a certain drawdown level to be determined, then the RO should be activated and used to supplement the drinking water for the rest of the summer to prevent that well from running completely dry. After speaking with the manufacturer, it was recommended that the RO is run at a frequency of 54 to 60 hertz for the best health of the membranes. At this frequency is less likely for particulates or small things to get stuck in the membranes and keep them not clogged. We also recommend to regularly backwash all the filters and the membranes of the system. Brooke covered these various membranes in the schematic, and they are prone to clogging. So keeping those backwashed as well as flushed with fresh water to kill any potential marine microorganisms that may have found themselves in there is a good way to keep these filters clean and happy. Furthermore, once the RO is activated in a particular season, it should be run every day or almost every day to prevent those membranes from fouling, which can happen if they are left to sit too long. And it should also be run for longer periods of time per day in order to improve that efficiency and realize the most out of the energy use. Finally, as I'm sure most of you are aware, SML follows some pretty fun and stringent water use policies. The tried and true, if it's yellow, let it mellow, and and not letting water flow unused. So we strongly recommend we upkeep those practices to reduce the water use on the island.
And the third project our engineers are going to be talking about is the new wind turbine, which again, you will see a video that I made on this topic.
Sorry to break in here. We're actually going to pause and do the first Q&A session right now.
Thank you, Katie.
Yep. So if folks have questions that you might have written down, you can use the raise hand function, which is under reactions down at the bottom of your screen, so that we can sort of have a orderly calling of people to ask questions. Thank you. Yeah, Ross.
Yeah, I'll ask a question. Why do you guys, I guess I didn't realize that the RO used less energy as it was used more. Why do you think that is? Did you look at it?
That's actually not something I had realized until I actually looked at that data that fluke meter collected. You know, I'm not actually sure, but I imagine it has something to do with the efficiencies of motors and how they operate over time. Perhaps it takes it takes a stronger power draw in the beginning to get them running up to the frequency that it's set at, and then once it settles into that rhythm, it's easier to maintain. But I'm not 100% sure.
So that graph that you showed, was that from the fluke meter, or is that something that you plugged in some values? Because I saw on the fluke data that you sent me, it had a min and a max and a mean. Is this something from this graph here? Is that from the download from the fluke data that you graphed, or is that?
Yes, it is.
Yeah.
It is, okay. Because I took that as like the min and the max as the VFD was ramping up, and that's where it kind of got the low end. And then when it came up to speed, it got the high end in hertz, in, you know, amps and volts and everything. And then, you know, there was a mean there. But you're saying that this is actually like over time, this is what's happening.
This is over the course of about 1 hour. Over here, down here, it's about 150, and then it's about 245 over here.
Yep.
So it definitely, this sharp spike in the beginning seems to be the VFD increasing the frequency at the beginning, but over the course of the hour of its use, it actively reduces the power draw, which I was not expecting.
All right. Yep.
Jen was next. If Ross is all good.
So do you guys want Katie May to manage the calling on people?
Yeah, absolutely.
Okay. Okay. And I just wanted to make sure everyone saw that on the Zoom call, it's the reactions tab that allows you to raise your hand, just in case you're not familiar. So my question is, we've thought a lot about the reverse osmosis, or how it's been described to me is to be used when we're not using power for something else, so that we've charged up all the batteries, and then we have, you know, what I would maybe deem free power that we might be just spilling at that point. So when I hear you talk about the cost of running the RO, how do I sync that with that understanding of maybe running it during the time when we don't have anything else to use that power for? How do I sync up that bit of information?
Right. So what we know right now is that we really only need to run the RO about 2 hours a day to produce like the amount of potable water we need for the residents on SML, just because the well water right now is contributing more than enough of potable water usage. So right now, the only way that I think that we're being able to be like energy efficient is by running it for 2 hours as opposed to 7 hours a day. But yeah, Zach, do you have anything you'd like to contribute?
Yeah, so it was suggested, you're right, Jen, it was suggested by previous interns to use that RO in the afternoon or the earlier to late afternoon while the battery capacities have been filled and we're just wasting the solar energy being produced. And while we would recommend to continue doing that, as we introduced at the beginning, one of our projects is to reduce that reliance on diesel generation. And by doing so, we're going to recommend a little sneak peek. We're going to recommend that you increase the battery capacity. So with that increased battery capacity, that excess generation of solar may no longer be there. So at that point, it would be recommended to use the RO as sort of a backup.
Mhm.
Awesome. Alec, I believe you're next.
Thank you and good evening. I just wanted to circle back to the fridge, just because it's such a great point that we can make in terms of conservation. If we go back to the initial slide that Jen showed, conservation is part of like almost half of how you've managed to get that diesel generator down and get to more renewable energy. So don't sleep on conservation. I'm curious in regards to the fridge itself. Are there any specific design aspects of the fridge that it is new that we can point to that show why it's so much more energy efficient than the older fridge? Are there aspects in terms of insulation or things to that regard?
So the old fridge was installed in the 1970s. So it was like 50 years old. So it was being very, very inefficient. And I think just having an updated system was able to increase the efficiency by 2/3. But I could also pull up a bit of the model and look into that if you're interested.
Yes, please. I mean, the age certainly is a factor. That's something we talk about all the time with our own customers.
So Alec, I can just go in 2 cents here is the doors got replaced. That was the other thing, not just the energy, running equipment, but the seals on the old doors were pretty bad. There was always ice between the freezer and the walk-in because of all the leaking out of energy from the freezer. And of course, like anybody knows, an old refrigerator with bad seals is gonna create the refrigerator to run more. So that was the other improvement that got done in that upgrade.
Gotcha. Thank you.
All right, so Glenn is next.
Yeah, hi, thank you. Just a couple of comments and perhaps some questions to feed off previous people's comments as well. When you look at the RO power draw, because of the way that y-axis is scaled, it's not an incredible savings. You're dropping from like 4.3 to 4.2. And it looks like it pretty much plateaus there.
Yeah.
So, running that for a longer period of time, I'm not sure how much, it's still going to be an incredible energy draw compared to the well. So I kind of agree with Jen there. If you can run this when your supply of power exceeds your demand during, very sunny afternoons when your batteries are full, if you can go ahead and run this RO there, but still you still have to create that balance or think about that balance about how much energy this is really drawing compared to your well, which is less than 1 kilowatt. And this is still, even at its max here, it's not even a 10% savings here over time, even though it does become more efficient. And then back to Alex's point on the refrigerator. Don't forget about conservation. And for the staff, there probably are some, most of that conservation, if you think about it, it's changes in behavior. And I think behavioral changes in the kitchen could help as well there in terms of, like you guys said, the number of times the doors are open, but also a full freezer and a full refrigerator are more efficient just because they're filled with materials that are the same temperature as what the freezer and fridge are trying to regulate versus airspace when hot air, warm air gets in there. And also things like eggs are sterile. So it's not a big deal that they be left out for a while. If you think about it, inside that membrane, eggs are sterile and they don't need to be rushed right back into the refrigerator. So, just behavioral changes like that could help as well.
That's a good point. Thank you.
Glenn, the eggs go into the reach-in refrigerator, so we couldn't save on that one, not with
Okay.
eggs, but That's
Well,
good.
I'll think of something
Yeah.
else that's sterile and let you know.
Okay.
Actually, I got the mic here. Chris, go ahead. You know, July, I don't know what it was on the islands, but, you know, July was one of the wettest months in decades right here. Was that the case on the island? And why were you running RO during the month of July?
Yeah,
Right.
so, oh, sorry. So yeah,
Sorry, I think my microphone wasn't working before. We only have about 5 minutes left in this section of Q&A, so I was hoping to get to the next 3 people. I'm sorry to cut you off, Glenn and Brooke. But yeah, if we can get to Dennis, John, and then Amanda, that would be great.
I just have a comment. Is it possible that the initial high energy consumption that is observed in the RO system is due to the buildup of pressure? More energy is required to initially get the pressure up for the system to be operating at that high level.
Yeah, that's definitely possible. And as I was, discussing with Ross earlier, the frequency of the machine needs to ramp up in the beginning as well. So it's during that sharp incline, it's that frequency in the variable frequency drive is actively increasing the hertz of the system up to its run settings.
yeah.
That's a good observation.
And even just going from like the pressure pump to the pressure manifold, it increases from 60 psi to 600 to 900 psi. So there is like a huge jump.
Yes, right. And I wonder what percentage of the seawater that goes into the system comes out as fresh water?
I believe the product flow or the drinking water is anywhere between 3 and 3.5 gallons per minute, while the brine or the reject flow is usually around 7 to 8 gallons per minute. So it's maybe 35 to 40% is the fresh water.
Gotcha. It's higher than what I thought it would be.
All right, so it looks like John put a hand down. So Amanda, will you go next?
Yeah, absolutely. So hi, I'm Amanda Goke. I'm a reporter with the New Hampshire Bulletin. I was really curious to learn a bit more. This is something it sounds like you're going to get to later in the presentation, but I was curious how much battery storage the island currently has, and like how long with the sort of demand like that would last for. And I ask that in part because I'm interested in this microgrid example, as you were mentioning, and how this can be a model for other areas. And one concern that people have with areas that have high renewable generation has to do with reliability. So I was curious if you have any insights into that and what, how you manage those elements on the island.
Yeah, if you are able to stick around, we'll kind of directly be addressing that in our fourth assignment. So we'll talk about that directly if you are able to hang around until the final project.
Okay, seeing no other questions, let's move on to your next part. Oh, Ross.
Yeah, I just wanted to address Glenn's comment about the running the RO in July. Glenn, as they mentioned in the presentation, once you get the membranes wet, you have to use the machine. So when we thought of this project, certainly on a typical summer, as the summer goes on, July is pretty dry, and we were hoping to see how the well was decreasing and needing to produce RO water, how that interaction would be. This is an unusual year. We really didn't need the RO, but when you start it in June, thinking that because it's a smaller machine that we're going to need to make water more over a longer period of the summer than like the old RO, which was much bigger, and we could keep up with demand very easily by starting it in July if needed. But yeah, since we started it when it was dry, the well is filled and it's full now, and it's gonna get winterized next week, so. We don't want to run it, but we have to, otherwise the membranes will get clogged.
Thanks, Ross. Let's move on to the third project.
Sure.
Oh, wait, sorry. Is there a break here that's supposed to happen? I got a little confused. Jen, do you want to still take our break? We're at 7:25.
I think that would be good if it's okay with the interns.
Sure.
Okay, so who's got a watch on them? Because I don't. We have a 15-minute break right now.
Yes, come back at 7:40.
Come back at 7:40. Thank you. You can
Perfect.
mute your screen, stop your video, mute your voice, so you can do whatever you need to do. Like eat Shoals Marine Lab chocolate chip cookies. Welcome back, people, everyone. We will be getting going again in a minute. 1 minute. All right, it's 7:40. So we can start up with the second part of the interns projects that they're going to present. You guys can take it away.
Awesome. Let me pop this back up.
Okay, so the third project engineers are going to be introducing is the new wind turbine. And again, we're going to start off with the video that I made. Perfect.
Wind is a great source of energy because it is abundant and we can never use all of it.
So we installed the first wind turbine in 2008, and now in 2021, we've been able to, amp up the efficiency of our wind turbines quite a bit. And through the work that Zach and I are doing, we're able to see just how efficient the current turbine is.
Ever since about 2007, when they first installed their solar PV panels, Shoals has come a long way in terms of renewable energy reliance.
Our goal for Shoals is to reach about 95 to 100% renewable energy. So we are not relying on the generators at all. And right now, I think that we'd be able to get there.
As part of the Sustainable Engineering Internship, we were tasked with looking at this new wind turbine, which was just installed, and we're trying to see if it's producing the energy that it is rated for from the manufacturer.
We've done some graphs in the past few days where we're looking at like the theoretical power curve or what the specifications sheet listed it should be producing, and then we also graph the actual power curve of what it's actually producing over the past few months, and they are very aligned. So it is working up to code, which is very good.
So at Shoals this week, the wind turbine has generated about 30 kilowatt hours of energy per day, which in a residential home would take about 20 days to generate the monthly energy consumption of 600 kilowatt hours.
So overall, wind turbines are a lot more efficient than solar panels. In fact, they're about double the efficiency of solar panels, whereas a solar panel can produce about 23% of energy per day. Wind turbines can capture about 50% of energy.
As opposed to solar panels, which need the sunlight, which obviously is not out at all times of the day, wind can run during the day and especially at night.
As an environmental engineer and marine biologist, it is an absolute dream to be on this island. It fuels my heart just how the wind turbines fuels the world. Wow, was that good? That was it. That was so good. That was so good. Thank you so much, Anna, for embarrassing me. But no, now it's time for the Power of Wind assignment, which is our third assignment. So just to give you guys a little bit of background, Shoals Marine Lab operated a 7.5 kilowatt turbine from 2007 up until the spring of 2019, when the turbine started experiencing internal electrical failures. The unit was then replaced in the spring of 2021 with a 10 kilowatt Berge wind turbine and an upgraded VCS2 charge controller. So wind power contributes significantly to SML's green energy grid because it has the capability of providing power at night and during stormy weather when the island's photovoltaic systems are less effective. Under the direction of Professor Martin Wozniak and from the Department of Mechanical Engineering at the University of New Hampshire. We were asked to quantify the energy output of the new wind turbine and then compare those findings with theoretical outputs suggested by the manufacturer. Ultimately, our job was to confirm that the turbine is operating as expected and provide an analysis of the contribution wind energy is making towards Shoals net energy production. Since wind speed increases with height above the ground, it's necessary to interpolate wind measurements for accuracy. As a result, the wind speed taken from the radar's tower anemometer was adjusted to account for the elevation difference between the anemometer and the turbine hub, which was 54 meters and 36.4 meters respectively. And this was to accurately convey the correct wind velocity at the elevation of the turbine's hub. The relationship of the increasing speed and power to increasing elevation is commonly referred to as the 1/7 power law, which you can see as the alpha. So then this equation was then adjusted to ascertain the wind speed at the turbine. It's then the wind speed at the hub height equals the reference elevation over, the hub elevation over the reference elevation to the 1/7 power law, and then multiply that by the wind speed at the anemometer. So then the power equation here is used to determine the theoretical maximum output of power contained in the wind at a given wind speed for a turbine. So these values obtained within this equation is used to determine efficiency of a turbine with the actual power it produces. For us, the diameter of the new wind turbine was 7 meters, and then we utilized the air density of 1.225 kilograms per meters cubed, which was corrected for sea level. So the amount of power generated by wind turbines depends on density, velocity, volume of air, as well as the swept area of the wind turbine blades and the blade design. Due to generator inefficiencies, friction, blade design, wind turbines can only convert a maximum of 59.3% of the kinetic energy into mechanical energy, and this is known as the Bent's limit. Therefore, the coefficient of power is used to determine the efficiency of the turbine's power production relative to the maximum power available in the wind. So then on the left, or the right, the tabulated power curve shows this logistic growth rate, graphing the power output versus the wind speed. At around 12,500 watts, it reaches maximum power output. And we're not sure if this is just wind or if this is because of the coefficient of power being the theoretical maximum efficiency for a wind turbine that can convert kinetic energy into mechanical energy. Now, extracting data from the dashboard, and it was like 60,000 data points, we collected the wind speed from the radar tower and then its actual power output. So that wind speed from the radar tower was then adjusted to account for the decreased elevation at the wind turbine, which was utilizing the equation referenced in the slide previously. The actual power output and the wind speed were then graphed in conjunction with Berge's theoretical power curve, which was displayed on their website. And as you can tell, the actual power curve is highly correlated to the theoretical power curve, excluding some minor outliers. Now, while the average coefficient of power for the theoretical model was 24%, our average power coefficient was 21%. I'm sorry, I mixed that up. Our average power coefficient was 24%, theirs was 21. And so as a result, we are 14.3% more efficient in terms of coefficient of power. This might be because of a super windy, turbulent summer, and we recommend that interns in the future do more calculations to determine if this is entirely accurate.
So as Brooke mentioned, while we initially had realized that 14.3% more efficient turbine than predicted, we did run into a little bit of data snafu just a few days ago that we need to address. So the charge controller from Berge, which regulates the power output from the turbine into the battery bank, does not provide the power output data in a user-friendly way that can be displayed on SML's dashboard. So instead, we have another meter called the AccuDC that reads that charge controller and displays the data instead. It was initially assumed that the AccuDC had a constant offset, so meaning that even when the turbine was not spinning, the AccuDC was still reading a power output of about 0.3 kilowatts. And it was assumed that this was constant no matter the wind speed or the power output read by the charge controller. However, just a few days ago, it was brought to our attention and we realized that this is not the case, and we started taking data points to see what we could find. And we actually realized this chart and relationship on the right. So on the x-axis is the power output shown by the charge controller. We know that because both the charge controller and the AccuDC both have visual displays on them. So we took these data points by just taking a picture of the displays at the same time because they're updating so rapidly. We took a picture of the data points, and the difference between the AccuDC meter and the charge controller is on the y-axis, and the charge controller real power output is on the x-axis. So as you can see, it is a very linear relationship that as the power output increases, the offset shown by the AccuDC increases. Now, this means that our initial estimate of 14.3% coefficient of power increase, this means that our initial estimate that the turbine was 14.3% more efficient than the manufacturer specifications is likely incorrect, in that the wind turbine is likely operating within the manufacturer specifications or just under. This is something that we are aiming to update in the next couple of days before we submit our final report. Now, moving on to the total energy generation. As I mentioned, the values are off slightly, but regardless, as you can see, the solar panels provided the vast majority, almost 2/3 of the island's energy consumption and production over the course of the summer, while the remaining renewable generation was provided by the turbine at about 11%. The diesel generation for the 2021 season was just over 22% at 22.6. Now, finally, like to make some conclusions and recommendations on the wind turbine and its operation. For one, after speaking with a Berge technician, the manufacturer of the wind turbine, he recommended that we do our best to limit the turbine's free spin. And this happens when the battery capacity that the turbine is attached to reaches its maximum voltage and maximum capacity, and the generator disconnects and the blades are just spinning but not generating any power. While he said this is fine electronically, it may lead to long-term damage of the blades mechanically, and we want to limit this as best as possible. So we can do this by adjusting the float voltage or the set parameters of the solar and wind charge controllers on the batteries so that the interactions are more friendly and do not damage the turbine by letting it free spin. In terms of the data collection by the AccuDC and the solar charge controller, it would be considered to install a third-party software to directly read data from the charge controller rather than rely on the AccuDC. Or alternatively, the AccuDC could be appropriately adjusted using that equation found on the power offset graph. Using that equation that relates the power offset and the power output, if we can adjust the data read by the AccuDC to then show more accurate data on SML's dashboard. So either adjusting using that equation or simply recalibrate the AccuDC and continue to observe that power offset and see if it makes a difference.
So the fourth and final project is the green grid. I did not make a video on this, but I do have a final one, and the visuals in the presentation make up for that. So take it away.
Alrighty, so SML currently maintains 3 independent green energy grids that combined include 92 kilowatts of photovoltaic panels, 1 10-kilowatt wind turbine, and then 470 kilowatt hours of battery storage. But during periods of when stored energy is depleted, SML operates a 27 kilowatt diesel generator that's usually turned on in the night from 2 a.m. to 7 a.m. With the help of Professor Martin Wozniak and Lee Consavage, Zach and I looked into how we can integrate the currently independent green grids with the goal of increasing the percentage of Shoals electricity production using green technologies. Using data from SML's dashboard, we analyzed the current ratio of green energy to diesel-powered energy sources, and then determined what additional infrastructure is needed to consistently reach those 95 to 100% green energy utilization rates. Now, this is a very basic schematic that I made representing the relationships of the main grid, the K-house, and the radar tower. So the main grid supplies the majority of power for Shoals Marine Lab. And at rated capacity, at a maximum capacity, it has 65.5 kilowatts between the photovoltaic panels and the 10 kilowatt turbine. The K-House solar panels power the saltwater pump, as well as, or it powers the saltwater pump, and then that supplies water to the sea tables, the faucets, the reverse osmosis unit, as well as the fire hoses. And at maximum capacity, it can produce 29.4 kilowatts. And then lastly, the battery storage at the radar tower is outdated and therefore supplies inadequate power. As a result of this, the tower is always buying from the main grid during the summer, and data indicates it has gotten significantly worse. But at maximum capacity, it can produce 7.5 kilowatts of power, which then powers dorm 2 and 3, as well as the PK lab. To improve the current percentage of renewable generation on Appledore, it's necessary that we calculate how much the island is currently relying on diesel generation. With that said, we summed up the solar generation and the wind turbines, as well as the generator production, and we compiled it all together to obtain the total island green generation. With this, we utilize this as our denominator when finding the percentage of green energy versus the percentage of diesel generation. And as a result, we have our results at the bottom of this, which shows that the green energy percentage from July to August was about 76 to 78%, whereas diesel generation was about 23 to 21%. Our goal is to transition this from a 75 to 25 ratio down to a 95 to 5 ratio.
So as Brooke mentioned, the big money $100 question is how do we reduce diesel reliance? We can do that in a few ways, mainly these first three that I'm about to mention. One, we can improve the communication of the three green grids so that they are not operating independently as they are currently. If they can communicate better and distribute and take energy from each other when one grid needs it more than the other, then that would reduce the diesel generation and improve the communication and compatibility. Second, we can replace the very outdated batteries in the radar tower, which currently hold very little charge, as Brooke mentioned, and are constantly drawing power from the main grid. And finally, that radar tower batteries ties into this. We can increase the battery storage and the renewable generation to reduce that generator reliance in the night. Currently, the generators run about 2 a.m. to 7 a.m. every night because the renewable energy generation, mainly the sun and some wind, provide enough battery capacity to last us for about 6 to 8 hours after the sun goes down. But the goal is to reduce that time to as short as possible or not at all, so we don't need those generators at all. But by analyzing the total energy provided by the generators per night for the 2021 season, we were able to recommend battery sizes and upgrades accordingly. So here you can see, starting in this second column, this is the average generator use per night in the 2021 season. It provided about the generators on average this summer provided about 85 kilowatt hours per night. So in theory, if we were to increase the battery capacity by 85 usable kilowatt hours, then we can stop using the generators on an average night and thus only have to use them on days where there wasn't enough sun or it was particularly rainy or not enough wind was generated. To be safe, we also added 1 and 2 standard deviations upon this mean, as well as included this max value. So these would provide much higher percentages of generator reduction, up to upwards of 100% for that max value. But notice how much more battery capacity would actually need to be added. Another thing to consider is the usable battery capacity versus the installed battery capacity. Currently, the depth of discharge for the ECB batteries is only from 100 to 68% to improve their life cycle and their length of service. So that means that in order for us to obtain this usable battery capacity, we really need to obtain add almost 3 times that value to maintain the health of the batteries long term. So there's a rough estimate of the number of batteries needed to be added at the bottom based on the current batteries, the Absolute GNBs, which are about 7.5 kilowatt hours per battery. So in addition, while this additional battery capacity would is great, we need to be able to fill these batteries during the day and during an average day where we're going to be generating solar and wind energy. So these values are the remaining generation of kilowatt hours that would need to be provided in order for those batteries to be full and for us to actually make it through the night without using the generators on approximately this percentage of nights at the top. So that remaining generation needed was modified a little bit based on some of the data from the 2019 interns when they found that extra renewable energy generation not utilized by the batteries because the batteries were full in the early afternoon. That energy that was previously would have been ideal to use on the RO. That if that solar capacity could instead be utilized, it reduces the amount of PVs that we would need to actually install. But assuming that this is the generation needed, meaning the space between the current maximum battery capacity and the final battery capacity after the additions, this is an approximation of the PV capacities needed, calculated using a rough estimate with the help of Lee Concevage, using general system inefficiencies and hours of usable sunlight. Another thing to point out is the vast difference in these two values, these four values between this 99.4% renewable and 100% renewable, while it's only 0.56% of nights. In order to surpass that, you need a drastic increase in PV and battery capacity. And that's just because of those off nights where there's a storm for a couple days, a day, and you don't generate really any renewable energy except for maybe some wind. And you really need to rely on the battery storages over the course of a day or two. Now, in terms of additional battery storage locations, as I already mentioned, the radar tower currently has very old batteries that barely hold any capacity. So there are currently 12 batteries in the radar tower. There's space in there for upwards of 24 batteries, in assuming we replace the old ones that are currently there. So that storage capacity can be increased by at least 100% and stop relying on the ECB. And although ideally all these grids will be tied and this additional storage will just feed back and forth, whatever, all the grids will work together. Secondly, we have the K-House, which currently has lithium batteries, which were received as a donation from a Cornell alum. And while these are great batteries, they are not as easy to use or are not used as well with how SML wants them to be used. They are harder to track their state of charge, and their voltage quickly declines once they reach their lower end of capacity. So it makes it hard to tell how much charge is actually in the batteries themselves. So while it's not very sustainable to completely replace these batteries, if it's necessary to allow the batteries in the three grids to communicate with one another, that is what would be recommended. Otherwise, there is a room on the other side of that room in the basement of the K-House to fit an additional 36 Absolute batteries. And if those lithium ion batteries are removed, they could fit upwards of 72 down there. And these two battery storage locations combined could provide all of the necessary capacity needed for any of those scenarios mentioned previously. So the major takeaways for this is that there are options for reducing generator use depending on how close you want to get to 100%. While that 100% renewable goal sounds wonderful, and it certainly is, it's not necessarily feasible, and you have to consider the trade-offs of cost and battery capacity and infrastructure necessary to reach that 100%. As I mentioned before, just that difference between 99.5% and that 100% was a huge increase in PV and battery capacity. So utilize the existing space and infrastructure that we have in hand. There are old PVs on dorms 2 and 3. We can remove the panels, but keep the mountings and the electrical equipment to save money there. Use the battery storage, use the space in the radar tower that's already set up to handle batteries. The equipment would need to be replaced there because it doesn't match the Schneider equipment that we have here in the ECB on the right. But the area is available. I'd also like to point out that models are currently being developed by a couple of groups. Dr. Martin Wozniak from the University of New Hampshire is working with a couple students to accurately create a model for battery capacity and infrastructure that would be necessary to reduce this diesel percentage. And I believe a group from Revision Engineering is doing something similar. That's Lee Consavage had mentioned that. So while these are preliminary estimates to consider, it's recommended that we compare these results with the results from the model. And final takeaway, as I said, the closer we get towards 100% renewable, the harder it becomes. And I would love for SML to get there, but it will take a lot of infrastructure and cost.
Thank you so much for concluding that, Zach. And just one of our final slides is about future project suggestions. So unfortunately, Zach and I were only on the island for 2.5 weeks, and we were not able to get done or, look into other projects as much as we'd like to. However, we do have quite a bit of suggestions for next year's SEI interns. The first one is anaerobic digestion to sustain the kitchen's needs. And this is fully credited to McLean Cohane, who is the island engineer on Shoals. He has an idea of directly utilizing the biogas from anaerobic digestion of food processing and sewage to then produce energy for cooking and hot water production. We think that this would be really interesting to look into. And then also the brand new gym, we think it would be a really interesting social experiment to find a way to retrofit the cardio machines with energy producing generators to promote healthy and sustainable living while on SML. We do not think that this would really have any substantial contribution to the grid, but we think it would be a fun social experiment. And then last two things, we would like the future SEI interns to continue the monitoring of the wind turbines' power output. It was a particularly turbulent and windy July, and so as a result, maybe our coefficient of power was higher than we would have liked. Additionally, after finding out about the power offset inconsistencies, we'd like to look into that more. And then finally, once Professor Martin Wozniak and his students has the battery model up and running, we'd like to do further calculations to see how we can maximize battery capacity and storage on the island. And with that said, thank you so much for being a part of all of this. Zach and I had a great time this summer learning a lot about sustainability on Shoals. And with that said, stick around, please, because Anna will be presenting her final video as well as talking about her experience as a Sustainable Calm intern.
So I'll show this one last video, and then we will open the questions to the last two sections, but to the last two assignments.
I think Shoals is really cool because you're able to have so much firsthand experience with ecology as well as sustainable engineering. So for me, in particular, we're able to kind of use this as like a micro model for what sustainability would mean back on the mainland. And so as a brand new engineer, I'm able to look at the wind turbines and the green grid and make sense of it, whereas it would be harder to make sense of that in a usual situation.
I don't think there's anywhere else in the world where you can find a group of people that are as talented and as passionate and as motivated.
Shoals is so cool because here on Appledore, I feel like everybody is so passionate about being sustainable, and they're passionate about the environment, and they just care so much about trying to live as responsibly as possible.
Shoals is my favorite place in the world. It's hard to describe, but the energy here is just unmatched. Everyone is so driven and excited to be here that there's this electric energy of interest and curiosity and passion.
Sustainability means relying on basically just yourself and being able to take care of yourself or your own system. And here on Appledore, we do a pretty good job.
To me, sustainability means only using what you really have to. So whether that's making sure you're taking shorter showers or turning off the lights when you leave the room, little things like that that add up.
So sustainability to me means being able to live responsibly off of the land and resources that you have without exploiting them completely, and just being respectful to, the environment around you and trying your best to just take care of it as it's taking care of you. That was great. Take two.
Thank you so much, Anna. That was amazing.
Aw,
And
thank
now we're-
you.
Yeah, and now we're open for Q&A for our last 2 assignments.
So don't forget, you can go down to that reactions button to raise your hand, and then we'll call on you so you can ask your questions.
All right. Alec, would you like to ask your question?
Sure, I'd be happy to ask my question. I found the final presentation fascinating. The integration of the 3 separate systems is so directly tied to so much of what we do already, you know, sort of talking about all the rooftop solar systems that are out there and try and find a way to put those together and maximize their usage. Going back to the question I had during the first segment in terms of conservation, that number of 99.5% versus 100%, was any consideration of additional conservation possible that might help you bridge that last gap to get all the way to 100%?
In that respect, no. That was purely based off of the electrical use today and the energy that those generators provide from this summer. So definitely those gaps can definitely be bridged a lot easier by improving those conservation efforts, which will definitely improve the ease of reaching that 100% sustainable.
That could be a great project for future interns. And also, I just wanted to say, I love the idea of the cardio equipment getting turned into generations and seeing what that does. I think that would be an amazing project to see in future years.
It would be a lot of fun. Yeah, thank you.
Mike Rosen, you're up.
Sure, thank you. Thank you all so much. This has been great, and it's been a real pleasure working with the 3 of you, and this information is going to be very helpful for us. I'm curious, in the last presentation when you laid out solutions for us for kind of 100% green energy on an average day, and then 1 standard deviation, 2 standard deviations away from that, and then kind of a maximum of 100% all the time, so to speak. Which of those 4 solutions would you recommend we try for? We were going to set our sights on one of them. What do you think the best way to move forward would be?
It would be my recommendation to, I put in that average day as kind of just a baseline, but I would recommend you start with that 1 standard deviation value. As you can see, that approximate renewable percentage would be north of 96%. And the increase is not too significant from that average value to that 1 standard deviation. Obviously, it's going to be an analysis of how much the island is willing to invest in this, and how easily it can be implemented. But I would recommend starting with that single standard deviation value.
Great, thank you very much.
Denny.
Well, first the gym idea, which was interesting. Some years ago, I was at a science museum, and they had a bicycle tied up to a generator. And I got to tell you, you really have to work hard to light up a 60-watt bulb, but it would be a neat little twist to the gym for sure. This is just sort of a general question. What's done at Shoals during the winter months to do battery maintenance and taking care of the wind turbine and so forth? What's that procedure like?
So for the wind turbines, we winterize it completely. So we take down the blades and we don't utilize it at all. And I believe Ross can answer probably the rest of it in regards to like batteries, how we're able to winterize that, since I'm not there during the winter.
Sure. Yeah. Thanks, Brooke. Yeah, and I'll ditto on Mike. Yeah, it was really great working with the three of you. Thank you for all your efforts. All this information is so great, and it's nice to have, smart engineers out there focusing on certain projects that we just don't honestly have the time to do. And it helps when you pointed out like a meter is not really doing what we think it's doing. So now we have to figure out how to make that work. Thank you for your efforts again. And so for the winter, as Brooke mentioned, we started taking the blades down after the UNH air map pulled off the island and stopped doing year-round research on Appledore where they needed the power. And the wind, of course, is great in the winter out on the islands. So instead of beating up the wind turbine, we remove the blades now. We have lots of solar from the time when AirMap was there. So we leave a little bit of solar on in each of the three kind of green grids to keep the batteries topped off. And the batteries also provide energy in the winter for our webcam, which I'm sure everyone's looked at year round. It also powers some other equipment like computers and stuff so we can kind of monitor the systems, keep our dashboard going. We also charge our gators in the winter with a little trickle charger so that when we go out there in the off season, we need a vehicle to kind of move things around real quick on the tide because there's no dock. We have a vehicle available right away to move stuff. So they're sealed AGM batteries, so there's no real maintenance as far as checking levels and all of that stuff, adding water or acid or anything like that. So it's great in that regard. The maintenance is pretty easy on that.
Ross, you might as well go right into your question.
Oh yeah. Okay. So on this batteries, this slide again, this one standard deviation or the number of batteries added. Did you guys take into did you calculate the fact that the batteries in the tower are taking energy out of the ECB batteries? Yeah, I guess that would be the main thing.
So that I shouldn't say we directly analyzed that for this portion, but that was included as part of like the total energy total energy consumption by the island. But in terms of, in terms of the tower batteries itself taking energy from the ECB, that draw is not very high. It would only be a few kilowatt hours a day. I don't remember the number off the top of my head, but by replacing those batteries with fresh new ones, then they should be able to obviously eliminate that usage by the ECB. But that's actually interesting. I didn't think of adding that back in terms of energy use that would be able to be, in terms of additional energy use that would be realized by expanding the tower batteries.
Okay.
Yeah, and just to give everyone a background about this, so the tower has been buying from the main grid for during like the past summer, and it indicates that it's gotten significantly worse. So in July of 2019, it was taking 77 kilowatt hours from the main grid. And then in July 2020, it was taking 175 kilowatt hours. And then this year in July, it took 252 kilowatt hours from the main grid. So this pretty much indicates that like the average battery voltage has stayed the same, but it might imply that there is a set point issue as well. So yeah, we'll look into it for the battery capacity.
Yeah, so everyone, these are our oldest battery set. They were put in 2007 for AirMap's primary use, and they needed year-round power. So they, I guess I would say, abused the batteries to get the power they needed to do their research. So they were drawn down further, therefore decreasing their life expectancy, and it's no surprise that they're starting to deplete and need to be replaced. And we've looked into this very thing from past engineering interns and how we're going to recycle them and how it's done. And it's so we have all that information when it's time to do that.
Cindy, you're up.
All right. Good evening, everybody. Great job, Anna, Zach, Brooke. Good to see you all, and great job to the mentors. I have kind of a sort of an overarching kind of take home message question from you guys. So after spending the 2.5 weeks on the island and engaging in these projects, what was the biggest take home message for you? I mean, there's a variety of topics that you studied. I'm sure each of you had a different perspective that you're taking away. So what was the most interesting thing that you found from this work?
I think for me, I was able to realize how seamless it could be to transition to more renewable energy generation just with my own lifestyle. There's just a lot of utilities out there that are willing to do that for independent houses. And that was my main takeaway, is that this isn't impossible to do this work. And also, I think another takeaway for me was just, it helped me pivot my career goals a lot. Now I'm definitely more interested in offshore wind energy, and yeah, I'm interested in renewable energy even more than I thought I could be.
I would agree with everything Brooke said. I definitely think my career is going to trend more into the renewable energy portion. But yeah, like she said, it's really kind of just getting the knowledge out there about how manageable and relatively easy renewable energy generation can be, and how it's applicable to your own home. But that being said, you know, these calculations really, for me, drove home the point of it's getting over that hump to reach that 100% renewable, which is, you know, kind of, I feel like most people's go-to phrase or go-to goal is more difficult than it seems. While it's easy to implement renewable energy as a whole, getting that 99, 100% renewable is very difficult. And, you know, because of the non-reliableness of solar energy or wind energy, there might always need to be at least a little bit of reliance on fossil fuels, which is not what I like to think about, but it's somewhat of a harsh reality.
Yeah, I agree, Zach. So I think that just like the whole conversation of sustainability, it seems very all or nothing for the most part. You know, it's like you have to be fully 100% sustainable. Like if you drive a car, like you're going to hell. And I don't think that that's true. Like I think it's like you're able to transition as best as you can, and like that shouldn't scare away people who are new to the sustainability field and to that conversation. And so I think it's possible, while also still being reliant very minimally on diesel generation, but having solar and wind be the main drivers.
Definitely.
Mm-hmm.
Hey, Anna, what about you?
I have a few things to say, but I also have my 5-minute presentation after this where I kind of talk about that. Okay. So I will be covering it then.
All right, next up is Tyler.
Hey, Zach and Brooke, nice working with you this summer. It was a real pleasure. I was really curious about the AccuDC versus Berge graph that you put together in short order. Yeah, I was wondering if you could go back to it. And I was curious, does this include values where there was 0 wind? Like, do we have an additional weird offset coming through as noise on the AccuDC?
I think a couple of these values are lower and closer to 0. But I know you had that initial offset that was originally implemented, that 0.23 kilowatts was, I believe it was just a combination of you, Mike, and Ross observing that when there was 0 energy production. Excuse me, 0 wind turbine rotation. So we didn't have any particular data points for that once we had realized that was a problem, that this data offset was an issue. But that's definitely something to continue to look at. And clearly down here, the offset is less. Some of these offsets are not exactly in line with this trend line. And that may also be due to something we noticed when we were taking these data points, is that the AccuDC display updates twice as fast as the solar charge controller does. So especially in periods when the wind is ramping up or slowing down, that offset is much bigger or smaller. And so it's really it would be helpful to be able to read directly from the charge controller. But you had mentioned, we had talked about that third-party application that really wasn't necessarily worth the cost, but all things being said, more data points need to be taken to flush out this trend line and make sure we have a better idea on how this AccuDC is reading the charge controller.
Definitely. Thank you.
Hey, Eugene, time for your question.
Hey, real quick, I realize we're running out of time here. Great job. It's good to see you folks again. What do you see as some of the new up and coming technologies, renewable energy technologies that we might be seeing down the road that could maybe also help us reach 100% in the maybe, the 5 to 10 year range?
So I know that Berge has now a 15 kilowatt wind turbine. So once that warranty is done, which I believe is in 5 years, we could look into possibly installing that turbine instead, or installing that in addition to the 10 kilowatt turbine. Other than that, looking into other renewable energy technologies, I mean, we could install some offshore wind energy around Appledore.
Yeah. Well, there's also new types of batteries coming up.
Yeah.
I mean, we get Elon Musk to donate a few Teslas, or
There you go.
And just so you folks know, we have a new engineer coming to Cornell who we're interested in some wave energy off the ocean. So yeah, lots of options. I just wanted to throw out there that it's not just optimizing what you have, but looking forward to hopefully some new technologies coming down the pipelines. But great job.
Thank you. Definitely.
So I think this is a good time to throw it back to Anna for her wrap-up presentation.
Perfect. Okay. Well, I do not have a slideshow. I'm just going to be talking for a few minutes. But again, hello, I'm Anna. I'm a senior at Cornell. And I was this year's Sustainable Communications intern. So basically, I'm just going to talk very briefly about my background and why I kind of got interested in science communication and why I'm basically here. So I went into Cornell my freshman year, very determined to go into academia, to go into research. And then I went out to Shoals after that summer as a student, and I stayed there for a bit. And then I came back to campus and I joined like a few undergraduate research lab. I was doing a lot of research work back on campus. And then during the pandemic, I had the opportunity to do a virtual data analysis research internship. And I think that's kind of where I first realized this huge gap between like science and like the people. I was experiencing like being able to see like all this like research that scientists were coming out with, all these cool discoveries that they were finding. And I felt like not a lot of people in the public actually knew about them. And I felt like I wanted to like bridge that gap between like science and the people. And then like around the same time, quarantine hit and I was very bored during quarantine, as we all were. So I started to pick up like videography as like just kind of like a hobby. I taught myself how to do some quick edits here and there, nothing too special. And then I think that also made me realize like the power of video. Someone can like sit down and tell you like, oh, the ice up north is melting. And it's like, wow, what a shame. But if someone like sits down and shows you a video of like the melting ice caps and like polar bear babies like drowning and starving, you're like, oh my gosh, like this is such an issue. And I think video is such a powerful tool because we are such visual creatures. And so I think, my realization between the gap between the people in science and videography kind of came at the same time. And then I kind of found myself applying to this internship and wanting to use videography as a tool of communicating why Shoals was so cool and why they're doing such cool work. And so, well, I hope you guys enjoyed the videos. There were 4 of them, but they were all very different styles, and I think that was me trying to make an effort to like, I don't know, first of all, like convey different styles, see what I could do, what I was capable of, but also at the same time, also acknowledge that people are very different learners. I think some styles connect to others more than like the other kinds would. So it's been an absolute pleasure working with Brooke and Zach. But at the end of the day, I'm not an engineer, I'm just communicating what they're doing. And I think a big part of this internship was thinking, okay, they're working on a new refrigeration system at Shoals. Why should people on the mainland who are not engineers, who don't know about Shoals, why should they care that Shoals Marine Lab just installed a new refrigeration system. And how can I convey that in a way that would make it interesting? And like the first video you saw was, it was a very quick, a lot of text and stuff. And that was actually inspired by an Apple ad back in 2017. And it gets you really excited about the fridge. And, I think my main message that I wanted to convey there was, you can switch out your own home appliances too and save a lot of energy and money. And this is how Shoals did it. And this is the result of it. And then for the second video, like, why should people care that Shoals is using salt water to make fresh water? And I think it was that concept behind it. Like I said in the video, like an RO isn't going to change the world, but the thought behind it will. It's kind of like how you take the solar energy and like make that and crank that extra energy by putting it into like making fresh water. And I think that whole like concept of like not trying to waste a single drop of energy, I think that was extremely relevant to anybody. And then my third video with like the wind, that was more of like a dramatic buildup, very different style than like, say the first fridge video. But that's also like, why should people back on mainland who aren't engineers, who don't know about Shoals, why should they care about a new wind turbine on this remote island, 7 miles off the coast? And, at the end of the day, I think solar panels are like really popularized. Everyone knows that solar panels are good. And I just kind of wanted to show an example of how the wind turbine at Shoals, like it's just one wind turbine, but it's doing such a good job of cranking out energy when, maybe the sun's not out or it's super windy or something like that. So it's just like this whole internship, I think, goes beyond just like these few projects that the engineers were doing, but it was also like, I was constantly thinking like, how can I relate what the engineers are doing and relate that to people who are in a totally different, sector. And so this is obviously, it was my very first internship in terms of the communication sector. I'm very used to doing research work. So it's been an amazing experience. And, it really solidified that I do want to go into science communication and maybe possibly use videography as a tool for that. So that has been, honestly, it's been amazing working with everybody at Shoals. And I am so grateful that I got to experience that, because I'm really excited where my career could take me. So that is it from the communications intern.
Thank you, Anna. Thank you all for great presentations. I feel like ending on that note, Anna, was fantastic. Just the impact of this internship and what you three just did is now magnified. There's 64 of you that have helped build the sustainability of this island, which is being interpreted off this island. And it's just incredibly impactful. And not only are you literally helping us, but you are helping the wider seacoast and beyond. And all of the grants and other things that we have happening now at Shoals are happening because of this internship program. So I hope you feel a lot of pride around sort of standing on the shoulders of all the other interns who have come and just keep progressing this place. So your names are now added to the 64 names that are on this plaque that ends up on the island. And it says at the top, in appreciation of Unitil Corporation for the student scholarship support of Shoals Marine Laboratory Sustainable Engineering Internship Program. And this program was initially set up in honor of a former CEO, Michael Dalton. And it has grown from that seed into this wonderful program. So thank you, Unitil, for making this possible. Thank you to all the mentors who gave of their time and wisdom and help to help the students address these problems and again, contribute to our success and the success beyond this island. So lots of praise and lots of hard work went into this, and we are deeply appreciative at Shoals for helping us. And I hope that you three will come back to next year's and maybe beyond to see what happens with your data as it gets progressed forward. And you can watch, it's not many places where you get to see the impact of your data move forward. So I hope that you'll join us next summer for this, and all of you join us next summer for this program. Thank you all so much for your wonderful questions and your attention and your participation. was great to see everyone. Many familiar faces. Thanks for being here. Everyone have a great night. Thank you.
Thank
Good
you.
night,
so
great
much.
job.
Nice job, everyone. Thank you. Thanks for everybody for coming and joining this. Hopefully next year we'll be on island.
Thank you so much, Ross.
Thank you.